So hi everyone, thanks to Sasha and the organizers for the invitation. By and large today I'm going to be talking mainly things that are rather introductory, rudimentary, and some maybe a bit, might even say too elementary. But I want us to all be on the same page because along the way I'm going to be saying things that maybe, by looking at where you guys come from and the kind of research camps you're coming from, I tend to think that there might be things that us in the community of numerical relativity have some other ways of doing things, and we have some reasons. I'll try and explain what those reasons are. Along the way, I might actually kill or push some sacred cows that people in astrophysics are very fond of, and they have very good reasons for that. And I'll just tell you some of our takes on that and how we got to that kind of situation, given the kind of problems we typically deal with in numerical relativity. So, but let me just try and say what the kind of schedule I'll follow. So today, so lecture 1 will be essentially about the basics. I'll talk quite a bit about numerics. And maybe as we go, depending on how we're going, I'm going to start talking about numerical relativity and what it entails. So in lecture 2, I'll talk about formulations and why we actually talk about different formulations and what might be more useful to you depending on what you're doing. And then, of course, this will fall into particular applications. And lecture 3, I'll try to make a connection with the main topics of this course, which is MHD and, well, plasmas in general. Because in all of these, I'll be referring to the other speakers. We're going to be going much more deeply into these. I want to give you enough information for you to think about the next steps, which is, as you know, gravitational waves have been measured, multi-messenger astronomy is with us, and there is a lot of work that needs to be done to try to understand the behavior of, say, matter and fields in the strongest possible regimes and how that channels some emissions that we can observe, and from that then do the inverse problem and try to understand the behavior of the source. And there are two communities, obviously. There is a community of astrophysicists and there is a community of people doing GR, or numerical relativity. Those of us in that community have been trying to bridge into the astrophysics are, by and large, very limited in our knowledge, in our abilities to connect not only to what's going on in the source, but how and what you're going to be seeing at a particular telescope. By and large, the knowledge of that lies on the astrophysics community, and then this interesting interplay is happening. But if I have to admit, my fear is that the astrophysics community will just take over and we're going to be completely on the sidetrack. And that's just fine. It's life. So anyway, so what I'll be trying to tell you is some things, especially on the GR side, so that you can bridge on that side. Understand some of the things we're doing. If you are to grab a particular code that is out there, and the astro community is very fond of coming up with collective community-built codes, we're not that crazy about that for historical reasons and also practical reasons. If you have questions about that, ask me. But so that you can interface with some particular group and understand what they're doing, where they're coming from, what's in the inner engines of those codes, and then think how you can put everything together. Stop me at any time. You're driven the lecture. I'm not the one driving the lecture. We run this seminar series at Perimeter where the speaker only is allowed 10 minutes. They're supposed to give the punchline, and everything else has to be driven by the audience. So it leads to a very interesting discussion. So I'm very fond of that model. Okay, so let me start now with this. And when I mean basics, I mean really very basics. So I'm going to take the simplest possible equation. Like so, many of you will know this, So sorry if I'm repeating things that you know very well, but as you know, I have a plan. I'm going somewhere with this. So let's think of this equation. This is the advection equation. You know what the general solutions to this problem is, and the problem, a general solution will be of this type, where f is any general function that will be determined by your particular initial conditions. And let's for a moment assume that there are no boundaries in the problem. So this particular equation has several characteristics, but one of them is that all perturbations propagate at the same speed given by lambda. If you now contrast this with the following, and of course you recognize this as some sort of kind of related to the Burger's equation, or you can even say it's a Burger's equation. Now the only thing I have changed is instead of having lambda, which in this case was a constant, I'm going to put the function u. Now the propagation of this equation, to understand it, is a bit more tricky because this is a nonlinear equation. There is so much we can do with a full nonlinear problem. So we understand this we analyze this by saying, well, let's concentrate on perturbations of a given solution. So let's imagine that u0 is any solution to the problem, and then we want to understand how perturbations of that will propagate. So let's imagine that now we're looking for a solution. Let's give u0 plus some delta. Delta is that perturbation we're trying to monitor. If I plug it in here and expand this to first order in delta, then the equation of motion I end up with is the following. So now at least the good thing is that we're looking for the behavior of delta, and we have by and large uncoupled it with respect to the u0. u0 is showing up in two ways, this term and that term. The term that contains the variable we're interested in, differentiated, is what we're going to call part of the principal part of the equation. And the rest, we're going to be kind of in a pejorative sense and just call them the lower order terms. We're not really we're not going to be caring that much about them. If we ask specifically about how particular modes of the solution to this equation, and this is, you can imagine, just even if you put a constant here, or some given function, say, of x, the perturbations of this equation, the solution to these equations, will propagate by the properties of this u0. The particular solution will be determined intimately by this term, but perturbations are governed by the u0. So now the difference is that depending on the profile of u0, delta will propagate a different piece of delta will propagate at different velocity. So if u0 had, I don't know, a shape like so, now, for instance, at that point, there is no velocity, there is no propagation velocity. That solution or that piece of the solution just stays put. And here we're either going to have one of two phenomena, either a discontinuity, a shock, or a rarefaction, depending on the signs. The good thing for us in the general relativity setting is that the properties were closer to this type of equations than to this type of equations. This is what you have, most of you would already know and be working with. It's the fluid dynamic equation, relativistic hydrodynamics, is described by this type of equations. Well, general relativity, which is a very special theory, is closer to this one. I.e., the speed of propagations have pretty little to do with the physics of the problem, the physics of your solution. The propagation will be given by essentially two possibilities, the speed of light or coordinate speeds. And of course, the latter one will be a tricky issue, but the former one will let us do a lot of things that typically we don't have to worry. Typically, you do have to worry a lot in this case, but not in that case. So, for instance, shocks and all the nightmares they bring, those we can get away with. They are not to happen in general relativity. And we're familiar with that. We're standing on a very huge discontinuity in the density of whatever of our surroundings. So the density of the floor is much, much higher than the density of the air. But if you were to measure the gravitational field across the floor, it would be just continuous and smooth. So that's a very, very particular useful property in the case of general relativity. Okay, so now why do we care about that? Well, I care because I'm going to introduce some concepts which then will be very important to us. Suppose now we have a system of equations, and for the sake of simplicity, we're going to keep thinking of one dimension, and for the moment also not worrying about boundaries. And let's say you have a system of equations. So I'm going to think that we have many variables u, which are governed by an equation of this form. Then we're going to see what conditions we want to ask. Sorry, this is not AX. It's A. It's a matrix A acting on the gradient of our unknown. What conditions we want to ask to that matrix A to be able to say something which are strong, some strong conclusions with respect to the systems we're dealing with. So the first one is we're going to demand that all eigenvalues of A are real. If not, I'm going to come back to this in a second. Suppose we have this equation. So I have just a real, imaginary eigenvalue, and then let's say we have it's just a one equation. So let's try and understand what the typical solutions of these equations would be. There's a linear problem. I can use a Fourier decomposition. Let me imagine that I'm going to write it as some function of t times e to the ikx for whatever wave number we care. I plug this in here. I'm going to have an equation that says the time derivative of f is minus kf. So the solution to this problem will be f is some factor times e to the minus kt. And I never said what sign k has. Sign k could have positive or negative sign. So if we were to be looking at a k that is negative, this is a blowing up solution. Blowing up solutions, that's not a problem in and on itself. We definitely can have equations of motions of a given system where the solutions should blow up. The key observation in this is that it's blowing up at a rate given by k. And so this is the first concept I'm going to introduce. It's a concept by Hadamard in the early 1900s. It says any physical problem should obey the following three conditions. So the first two are obvious. One, existence of a solution. Two, the solution is unique. And three, the solution should depend continuously on the initial data. And what this is kind of a bit contorted, the way it's expressed, but what this means is the following. Take an initial configuration, any one, obtain the solution after some time, I don't care how long, just it could be even very local in time. Now take exactly the same initial data and perturb it in an arbitrarily small fashion. Would the solution at a later time be sufficiently close in a way that one can understand to the previous one? And by sufficiently close, well, there is a mathematical statement with respect to a Sobolev norm. You just want the solution, let's say, u1 minus u2 at times t, be bounded by a factor here and a factor there times u1 as 0 minus u2 as 0. And this is in some Sobolev norm. So let me just say, put T here. I'm going to put a Sobolev norm here. The Sobolev norm is something we don't typically worry that much in the context of numerics. But this says, well, given the initial data, so if you have any data that belongs to some Sobolev norm, says you not only have control on the data, but also on derivatives of the data, and you want to know that at a later time, your solution still belongs to the same norm. But the key thing of this relation is that neither gamma nor beta should depend on the initial data. And in this particular case, we have a growth, if k is negative, that is intimately dependent on the initial data. That k is defined by the Fourier terms, so the Fourier modes of our initial conditions. Is that clear? Okay. So this is going to be our driving principle. Everything else that we do will be always trying to follow this principle. And in fact, I told you one of kind of sacred cows are just push. I give it a nudge. Not to say there is anything wrong with it, but I'll mention later in the final lecture, how a very dear technique to deal with plasma called the constraint transfer technique, and lots of excellent results have been obtained with it. One reason to using it is because otherwise you're violating this condition. But there are other ways to satisfy the condition without using constraint transfer. So 2 weeks ago, we were at the KTP. I was making the following joke. It's not a good joke. I'm not a good comedian. You know that people say that any result obtained by a theoretician, a theoretical result, is believed by no one except the person who got it. Any result that is obtained experimentally is believed by everyone except the person that got it. I would say in computational physics, you shouldn't believe the result that anyone got at the bleeding edge of physics, if he hasn't, bleeding edge of computational resources, if he hasn't been supported later on by another simulation that is far from just pushing the limits of your resolution and resources. So, and there are many like this. There are computational physics or numerical techniques are unfortunately filled with old wives' tales. Many of those tales are because you had to introduce very particular tricks that work at that time or were necessary at that time because you were working at the limits of your resources. 1 year later, or 2 years later, sometimes many of those things change, but the myth of the ledgering stays for a very long time. I'm not sure if you disagree with that, but I'll give you examples. Okay, so that's our first condition, because if any eigenvalue it has an imaginary part, then we're doomed. We're going to go back to that problem. And I should stress, notice that we're talking about first order in time, first order in space systems. So that in your case, or in the case that you are probably most familiar with of hydrodynamics, that's precisely what you're dealing with, unless you introduce dissipation or viscosity in the problem. But if you don't, you're already working here. In the case of general relativity, you're dealing with second order equations, second order in time, second order in space. And you either have to bring everything into first order form, or they are analogous definition for the second order problem. So I'm going to just stay to keep things as closely as possible to the case of hydrodynamics to first order form. So all eigenvalues are real. 2, we're also going to demand that the eigenvalues have an associated that all the associated eigenvectors are linearly independent, that there is a complete set of eigenvectors for this problem. We'll discuss why in a second, but let me just make a comment. Yes, so if you have a problem where all eigenvalues of your principal part are real, the problem is called, that is at least satisfying the property of weak hyperbolicity. if you satisfy the second property, you're either in a case that is strong, symmetric, hyperbolic, and the difference between these two, we're not going to care about. By and large, you get all the benefits regardless of the two. So let me give you an example. Have only two, yeah. To try and understand why we care about two and one might be difficult. So let's think of a case where all the eigenvalues are real, but we don't have a complete set of eigenvectors. So for that, I need at least two variables or functions that we're trying to obtain its evolution. Let's imagine the following expression. So we have that equation. So u comma t is given by u comma x plus v comma x, and v comma t is given by just v comma x. This is a very simple equation. You can put it in Mathematica. It will give you the answer in terms of some unknown functions, but let's just work them out ourselves. If I can find my notes. If not, I'm going to have to work them out again. So let's say, so from here, so this equation is equations that we have been discussing. This is just the advection equation. All is good. The solution to this problem is given by p, is given some function of t plus x. Now, when I plug this one into that one, I end up getting a source. And what you find out is a solution is of the form so it has a component that is the one you would have expected based on this part. But then it has a linear growth associated to the solution to the first equation, the equation that we saw for v. So now we have something that if we want to bound the norm of the solution with time, we know that we have a growth in time, which is linear. It depends on the initial data because it has f in here, and f is determined by the initial data we give for v. And you say, well, if linear growth is not too worrisome, and indeed it's not. But we have ignored the lower order term. What you can see in the case of weakly hyperbolic problems is that the lower order terms have a significant impact on the solution. Even a very simple lower order term of the form uv, or even u0, turns this solution into an exponential. And we're back onto the case that Hadamard would have told us that's not physics. So it either is a consequence of an ill-defined system of equations, and that could very well be the case, or the problem you're describing is not physically well-defined, period. Of course, it could be not physically well-defined for more than one reason. It could be not well-defined because the underlying equations of motions you're trying to solve have intrinsic properties or intrinsic problems, or you have not given the problem in full. For instance, if you're trying to solve the wave equation, just let's imagine you're trying to solve this problem in this domain. Well, you know you need to give two boundary conditions, and on the initial hypersurface, the value of the function and the time derivative of the function. If you don't provide all the necessary conditions, you're not going to be able to satisfy uniqueness of the solution. But Hadamard tells us if you don't pass this condition, then something is wrong. Pause. Don't try to force numerically something when already you're dead on arrival at the analytical setup. And the reason we in the numerical relativity community ended up having to worry about these things is because literally nothing was working in numerical relativity. The moment we moved from spherically symmetric situations to 3D, everything started to fail. And we tried all sort of tricks. All the old wives' tales came. We fought for a decade or so. But slowly, we started recognizing some of these issues. And the issues were, well, the formulation was incorrect. Was of weakly hyperbolic type, and I'll tell you, we'll discuss some of this later. The equations beyond that could be even written in a better form. And the underlying system or numerical techniques we were using could be made more robust. And these are the things I'm going to try and describe now. So now let's see what else do we gain if we're able to demand that our system of equations is at least of this type, strongly or symmetric hyperbolic. So we abandon these. I guess I could mention in passing, if you take the standard ideal MEZ equations, are of weakly hyperbolic type. The constraint transport deals with that at an algorithmic level. But you could deal with that at an analytical level, and to some degree be done with it, except at the cost of buying some other problem, which we'll get to later. So now let's assume that we have a complete set of eigenvectors. So what else can we do? Well, suppose we have, again, I'm going to write it this way. So we have a vector. And since I'm already thinking that we have a vector of unknowns, let me just forget about that supraindex. U is a vector of unknowns. So we have the lower order terms. This result tells us that we don't need to care about the lower order terms to discuss the main properties of the solutions we're dealing with. So we're now able to ignore these guys. So what else can we do with this? So one thing we can do is to say, oh, if there is a complete set of eigenvectors for A, then there is a transformation, let's call it T, such that T to the minus 1 AT is a diagonal. Okay, so let's use that. We can multiply, let's say, just give more space. So I'm going to multiply by T here, T to the minus 1. So this is my identity, so I haven't done anything. I put another identity here. I haven't done anything either. So now I can multiply by T to the minus 1 on the left. I can use the T to the minus 1 and the T to erase that part. Now this is our diagonal, and then I'm going to consider this part and rewrite it as what? So this is T to the minus 1 U comma T. Let me just rewrite it as T to the minus 1 U comma T minus something that knows about the derivative of T to the minus 1. But now I have something where U is not differentiated. So it belongs to the lower order terms, and we said we can ignore them because the properties of U. Similarly here, I can write this as T to the minus 1 U comma X plus something else where U is not differentiated. So again, we can shove it to the right-hand side. And at the end of the day, what we have is now a system of equations. This is V comma T is a diagonal V comma X plus a lower order terms. And so what do we have? Thanks to that property, we simply have a sequence of advection equations because it's just a diagonal. So we have a problem that looks simply like V1, V2, Vn, comma T, lambda 1, lambda n. So we just have a collection of equations that says v, let's say sub index I, comma t is some lambda I, b comma x. Any questions? Yes. So we're not dropping them when we look at the specific solutions. We're going to consider them, of course, when we're trying to deal with the problem. What we're allowed to, if we ask the following question, if I take a given solution and perturb it, because when we look at the characteristics of how things are propagating, we always think of perturbation. So the properties of the speed of propagation of the perturbations are independent of the lower order terms. Of course, the solution itself will be intimately determined by the lower order terms. But the propagation properties, which will tell us where and how do we have to give boundary conditions, what are the most convenient numerical schemes, what determines our, I don't know if you know the CFL factor, how big a time step we can take, that's all determined by the eigenvalues. And if we are in the case of a strongly or symmetric hyperbolic system, or system that has a complete and independent set of eigenvectors, we are justified in ignoring those, and the speed of propagation that we estimate is the one that you obtain from the principal part. If you were dealing with a weakly hyperbolic system, you don't know. That's the point. But absolutely, thanks for that question. That was a good one. So let me just mention some extremely useful resource on these. A lot of what I'm describing here is in this problem, these time-dependent problems on difference methods, Gustafsson, Kreis, and Oliger. If you don't know, I mean, those of us that are older in the audience know essentially a lot of the applied mathematics community owes very much to these, were the great-grandfathers. Many of the people you know they have introduced kind of very fundamental contributions to the application or the numerical simulations of complex physical problems can be traced to those people. So it's a very mathematically looking book, but it's very good. If you take your time, you're going to learn a lot. And the funny thing is this book over and over discusses that problem. So essentially just keeps talking about this problem back and again, just telling you how to come out with the right techniques and how everything can be based on a sound mathematical footing. Okay, where do we go from here? So then for a more kind of palatable discussion that might be more closer to the kind of questions and notation that we're more familiar with in physics, I would suggest this paper that we wrote some years ago, which also has all these descriptions in, I would say, in a closer notation to what you're used to. Okay, so what else can we do with this? So now we know that the system, in principle, is completely diagonalizable. If we diagonalize the system, then we recognize that we just have a system of advection equations. And by looking at the signs of these guys, we would know if the perturbation is moving to the left or to the right. That we can use to our advantage on the boundary conditions, or to understand whether, say, our coordinates are well behaved, and if we're dealing with a black hole, where things are falling into the black hole, and we do or do not need to worry about boundary conditions. So I'm going to keep pressing on with this line of thinking to see what else can we get out of it. And after hopefully convincing you that if we are kind of satisfying property number 2, which in reality we have is a series of advectionless equations. So I'm going to go back to the advection equations to forget about dealing with much more complicated problems and then try to infer further properties that we're going to use. Because we already know that what we're doing is just working with a collection of advection equations, given that we're dealing with hyperbolic problems. So at the moment, I'm ignoring constraints, things that will come out, but we'll try and deal with those as we go when we need to. So let's go back to the advection equation. So now let me try and introduce another concept. It's a concept that mathematicians like to introduce, which is the energy norm. These are things that, by and large, or in many cases, are exactly the same as the energies we consider, but in their case, they need not be related to any physical energy. So let's consider the following quantity. Again, we're thinking that we're in one dimension. And I'm going to try and say, let's imagine we have a boundary at left and right boundaries. So this, in particular, is a particular norm of the solution. This is the L2 norm of the solution. And we could ask, in the case, in the context of Hadamard, whether the norm of the solution is bounded in time. Again, if it is, the system is strongly or symmetric hyperbolic, which in this case it is, we're going to assume, let's say that here we have a 1, so that is a real eigenvalue. But we're going to learn more about this. So let's consider the time variation of this one. And I will very quickly be sloppy, if I hadn't already been quite a bit for your taste, and forget about factors of 2, et cetera, that are inconsequential. But so if I do this, that would be, just by definition, we're using the analytical expression to say something about the rate of change of the energy. So then I can rewrite this as lower order terms. Let me imagine that this is a function b of u. I can use iteration by parts here. So this is going to be the integral of dx of u squared plus the integral of ub of u. So this piece, now we know is u squared, left and right. So it will be the difference of u at the left and u at the right, plus something, so you have u times b of u. This typically can be bounded by some other function where u appears explicitly. So this, you're able to usually end up writing as this, u squared again, times some factor in front. So you end up with something that says E dot is less or equal to some number, which is given by what you put at left and right boundaries. So something plus something else times the energy itself. And this is implicitly already saying that we are satisfying Hadamard condition, because it will tell us that the bound, so from here we can integrate this explicitly, and we're going to show, we can say that the energy or the norm of the solution at later time is bounded by the norm of the solution at the initial time. Let me shove in here some other term. So suppose for the sake of the argument, you put in here some epsilon times the second derivative of u. So the only thing that changes is somewhere in here. I'm going to have plus dxx of u. We can again use iteration by parts. And what we're going to end up with here is something that will have minus epsilon dx of u squared. So the role of this term is to account for some loss of energy in the system. Of course, our problem might not have that, but it might be useful to keep that in mind. So let's imagine now that we're trying to go discretely. So I'm going to slowly try and motivate from what we have in here how we should be choosing numerical algorithm. And the reason behind that, again, I'm going to just keep. Are we being recorded? Is this going to be online anywhere? Okay, then I'm not sure what I'm going to say. No, so if you open books, and I'm going to use a particular example like numerical recipes, those are recipes. And they tell you typically, oh, if you do this, it's a particular method to advance in the future. There is very little support as to why you would go one way or another. And unfortunately, numerical applications are filled with that. But these guys, mathematicians, we're working really hard to try and guide us. And by and large, we haven't been paying much attention. And so I'm going to tell you one particular story, which I think is awesome. For those of us that started looking at things like, again, cooking recipes in the back corner, doing some black magic and trying to evolve, for all the time, someone to tell you, if you do these things are going to work. And since then, I haven't written a numerical code where I actually had to experiment with the numerical technique. I knew from the get-go what was the best path forward. So let me just try and tell you what those guys are saying. Suppose now we're going to try and introduce some discretization. So let's take, for the sake of the argument, a uniform grid. I should say, I'm going to keep the discussion centered around finite differences, which are not perhaps the most sexiest of techniques, numerical discretization options out there. But everything I say translates to, in one way or another, to other methods, finite elements, spectral methods, etc. But just for the sake of the argument, let's imagine we're introducing a uniform grid. So from left to right, we have a number of points. For the sake of the argument, I'm going to use also the grid is uniform. Well, it's uniform, and yeah, so we have x left, x right. The separation is delta x, and we're going to begin by taking the following assumption, which is we're going to assume that space is discretized, but time is continuous. I'm going to pull a quick on you in a few minutes, and then go to fully discrete in time and space. But let's assume this one first. So we're going to go back here. I'm going to try and say what kind of things were crucial for us in deriving this kind of estimate. If we have started, as I said, with a continuous time, this step would have been exactly the same. Modulo this integral that would have had to change that to a sum, right? I would have said, let's call this, or maybe curly, is the sum from I equals, say, 1 to n of ui squared dx. I can put a 1/2 on each side if I want to do the trapezoidal rule, but let's just keep it that way. So in this step, I took the time derivative. So it will be the sum again, 2 ui u dot. And I can do this because I'm assuming the time is continuous. The problem is when we get to this step, I use integration by parts. So there is a key step there where we say the sum of u, d of u of I. So here I'm dm using it to denote our discrete derivative operator, is given by, or is equal to, di of u squared. That's what we use here on the continuous level. This generically is not true when you choose discretization algorithms. However, this is what these guys did in particular, and then, or you can see here in the title of that paper is summation by parts. You can insist that whatever discretization you choose, whatever representation of your discrete derivative operator satisfy this property. Let's assume you do that. and I promise you can do that, then if that's true, we jump up to here because we're satisfying that condition. We recover that the contribution of the derivative part, the advective part, will be at the end of the day just the left and right values of the square of your field. And then you're going to have other things that know about the initial amount of energy that the system, or the energy the system has, and if you have dissipation, also some way to take energy out of your system. So there is a large body of work that started in the late 90s and is continuing to today, of people that come very much from this school. They keep producing these operators. And once you understand how to create them, it's not very difficult for you to also get involved and get your particular flavor that you like to use constructed. But bottom line, that's what these operators do. They satisfy this property, which allows you to recover some results that are very close to the kind of results you need to prove at the analytical level that the system you're dealing with is well behaved. But now you have to say, well, wait a minute, you did cheat to the bit because you use a continuous time. Well, there is a separate result. There's a theorem by Tadmor. And the theorem says if you use at least a third order accurate, so third order accurate, third order in time. So if delta t is your time stepping, so if different steps are separated by delta t, if you use at least a third order accurate time integrator, the continuum goes into discrete level. So I'll say a few more things, but I mean, I want to pause and really stress these. What these guys are telling us, and I can assure you in practice it works, is to say, well, work hard at the analytical level, make sure your system of equations satisfies this property. Use the derivative operator that you care. So if you want to get second order, fine, use second order, fourth order, regardless. But make sure it satisfies summation by parts. Iterate using a third order accurate or at least scheme, let's say you take Runge-Kutta, you put all that together and it works. So I'll give you some examples now, but there's a clicker here. Where is the clicker? I don't know. How do you go from one slide to the next one? I won't say there is a clicker. Doesn't matter. Okay, there is, Oh, okay, thank you. So I'm some suggestions for some of you that care, that want to play around with this. You could do the following. Take, for instance, a non-rotating black hole solution. If you don't, you can even start with a no black hole at all. Just take the simple advection equation, or just take the wave equation better. Reduce it to first order form. So let me maybe give you, so take this equation, reduce it to first order form. For that, you will introduce, say, a variable f to encode, say, the time, well, let me see, the space derivative, and the variable g to encode the time derivative. You can rewrite this system in terms of equations for f and g, that so as to be as close as possible to the rules of the game that we have specified, and iterate that. And I said, don't try anything, just use this operator, use this technique, and you'll see that it works. And then you can begin to climb the ladder, put a black hole without back reaction, put a black hole with back reaction, and then you can do the hydro, and if you want to go, you can go to higher dimensions, but this is just in spherical symmetry. So we'll discuss more of these things later. But so any questions here? I'll give you one example, or some examples now, of how these operators work. Yeah. Oh, it has to do with the estimate of how errors accumulate versus time and where you can maintain the bound on your energy. It's a, I mean, it's a complex theorem, but you're right. So second order doesn't do it. I don't know. I can check. I can check. It probably is related to. No, it's not related to the order of the derivative of your problem. So, this problem, these theorems go beyond just the first order representation of the problem. But I'll take a look. I mean, I can remember. Good question. There is a price that you pay to try and satisfy this property. Let's say if we stay with finite differences. So let's take the simplest possible derivative. So let's imagine we are trying to compute just the first derivative of your function u. And a second order approximation is at point I is u plus 1 minus u minus 1 divided by 2 delta. Let's say that will give you a second order approximation. And let's imagine now that you're taking that term. So let me just work out some terms, and then we'll see what we might need to add, or how we might need to define this d. So let's imagine that this d operates over all your internal points, and you still have questions as to how you're going to modify the derivative operator near the boundary. That's always a problem in general, in particular in finite differences. When you get close to the boundary, how do you deform your derivative operator, given that you're not going to have a point to the left? Let's say here the derivative at that point you get from subtracting these two. But when I need to know the derivative of this point, then the question is what happens there. And so you need to modify it. And you modify it how? Well, the first thing I'm going to say is the norm can have an arbitrary weight. So I'm going to put a weight there. So that's an area of the unknowns that you need to specify. Of course, you have to be positive. So you're defining the norm as the sum of sigma I ui squared. And then these sigma i's are greater than 0, delta x. If you think that sigma I being there is odd, think of the trapezoidal rule to iterate an integral, or performing an integral. The trapezoidal rule will tell you sum the function at every point and just 1/2 the function at the first and last point. So this is exactly the same. And in fact, there is a very intimate relation between rules of iterations of given orders and the summation by parts. So let's say I'm going to have a term that goes like u3, u4 minus u2 divided by 2 delta plus u4, u5 minus u3 divided by 2 delta. And let's imagine, so I have the sigmas. Let me imagine that the sigma I is equal to 1 for all points interior. So for I greater than some low number and I smaller than some other number. Sorry, 6. So now we can just go through by inspection. So I have a u5 times a u4 with a minus sign divided by 2 delta. And I have a u4 times a u5 with a 2 delta. So that term, this will cancel that. We have a u3, we have a u4 and a u3 with a minus sign, and I have a u3 and a u4 with a plus sign. They cancel. So if you follow this through, if you didn't have any boundaries, if this thing were in a ring, everything would cancel and you would satisfy the derivative, the summation by parts or integration by parts rule. There would be nothing left over for you that knows about any particular boundary as you would have expected. But you can find out that if, say, the only thing that you haven't defined well is sigma 1 for the first point, du1 times u1, then you can find out, you can easily find that if you define d u at point 1 to be u2 minus u1 divided by delta, and sigma 1 is 1/2. So that operator satisfies the properties we wanted. So the price I mentioned you had to pay is that this at interior points is a second order approximation. What we had to do at the boundaries is drop it to first order. Typically, that was not the MO of like this backdoor cooking particular ideas was. The typical thing you have said, oh, I'm getting towards the boundary, and I see problems. Typically, you'll see high frequency oscillations and then issues associated to what you're doing in the boundary. And the natural temptation was to say, oh, I have a lot of information to the right. Let me use more and more points. And then you have all this large number of points involving derivatives that were much, much more accurate. So derivatives of fifth order or fourth order, first order, the approximation to the first derivative of fourth order accurate in delta x to do that, and things would not help. This rule is going in the opposite direction. It's lower it, but then this works. And again, as I promised, this would work. And the other thing you have is, did I erase it already? Yeah. That you can have with these derivative operators is, remember, I said, well, suppose you had a piece like so. Analytically, we could prove that this takes away energy. If we try to reproduce that discretely, why? Because we may introduce artificial dissipation, and I'll tell you why, how this would work in a second. These derivative operators, this summation by parts operator, will also guarantee that you are taking energy away from the system. Because it might be that, again, if I discretize the second order derivative, I might be taking energy at all interior points, and when I get close to the boundary where I deform it, I actually am pumping energy. So this last piece on this. So let me just see. How many of you know about artificial viscosity, artificial dissipation? You don't know? Okay, one. Yeah, okay, but you would know. Okay, so in kind of going back a bit of history, in the 60s, people were really, or the US government really was interested in predicting the weather, and no code was working. And again, so they made a committee, they brought a whole bunch of applied mathematicians, and these guys were there, particularly Kreis. And so he introduced something now is known as Kreis and Oliger, the Kreis-Oliger dissipation. I'll explain you what it is, and then it took many lives of its own in the context of astrophysics or fluid dynamics, people to deal with shocks, discontinuities in the field that would kind of cause problems left and right, and we can discuss why. Then they started using artificial viscosity. It's something that goes in there to try to smooth out high gradients. Of course, in the context of fluid dynamics, that's very tricky because you might be killing the very process you're trying to model, i.e. a shock. But so in the 60s, they did this, they introduced this technique, and of course, after a few hours, there was no weather left. Everything was uniform because of how aggressive these things can be. But let me just explain you this and why we actually want to use it at some point. So take again this equation. And then what you could do is just think of it, the discretized version of this. So I'm going to call it dt of u, lambda dx of u. So I'm going to use now make a blank statement, but I'm sure I can defend it. No matter what technique you use, choose anything you want, you're going to miss the right behavior for the very high frequency modes. course, that's an obvious statement. If you have a grid that is, and you're discretizing with whatever method you want, the modes, like the Fourier modes at your highest possible frequencies are usually badly dealt with. And you can ask, what are those modes doing? And typically they do a few things, even in the linear problem. They typically are not moving at the right speed. So we know that here, every mode should be moving at the speed of lambda. You can actually compute through your discrete approximation what is the speed of propagation of each frequency. And you're going to get that typically, not only they might be moving at the wrong speed, they might actually be moving in the opposite direction. So you're representing them so badly that things are bad there. If you are now dealing with a nonlinear problem, so imagine you have a U square. That mode that is sitting at your highest frequency, when you square it, all of a sudden goes to the lowest possible frequency. Right? Do you see that? So that gets aliased. So just let's imagine the following case. This is our grid. What's the highest frequency that you can accommodate would be a solution that is doing this. So it's point-to-point oscillation. Now square it, and you just have a constant function there. Let's just go from -1 to 1 to that. So you went from something that was at the highest frequency of your grid, that you knew you were badly representing it. Now all of a sudden, because of a U squared that you may have in the lower order terms, it gets aliased back to the lowest possible modes of your solution, which are the ones that are supposed to be treated the best. So recognizing that, you say, well, given that they are bad, I'm going to do the natural human thing to do, is just go and kill it. And this is, again, all numerical techniques have different ways of dealing with it. If you're familiar with spectral method, they have the 2/3 rules or something. You take the 1/3 highest frequency mode and you throw them away. In these, but it could be in any technique, because I keep stressing, we think analytic first, we do numeric second. So I could imagine putting an epsilon here, and to make things dimensionally correct, I have 1/t, 1/x. If I think of t and x having the same units, I'm going to have to put some unit that goes like L. I mean, I need some L unit here that we're going to discuss in particular applications what it would be. So I want to put something there that dissipates the highest frequency modes, and this will do it. Right? This is if you forget about that, that's like a heat problem. It's a diffusion problem, and you know that the highest frequency modes are diffused first. Again, we can see this by imagine doing the Fourier decomposition again. So I take U as f times U times e to the ikx. We replace that in there. We're going to have lambda ik plus minus epsilon L, some L, k squared f. Right, and we can iterate this. This will give us f of t is e to the lambda ik times e to the minus epsilon times some length there, k squared t. And of course, out of this, u of t and x is e to the lambda I lambda t plus x. So this is something that, for the largest possible wave number, you're dissipating, you're decaying. So you're controlling the highest possible modes by having introduced a completely ad hoc term in the right-hand side. This was not part of your original problem. You put it in. So we have to worry about what is it that we're doing with the physics. We'll discuss that. But if we had such a case, then this will be one way of controlling the highest frequency modes. So Kreis-Oeliger dissipation is a thing that Kreis and Oeliger introduced back in the 60s to deal with high frequency contamination. And it goes generically on this form. Let me just do it's d to the 2p of u, so an even number of derivatives multiplied by some length scale to 2p minus 1 in the case of first order type equations. Of course, in reality, what you're doing, or what this technique calls for implementing, is the following. So you take your original equation and you add to it some factor there, so some parameter, which you can choose to be 0 just to compare with the no dissipated problem. Some delta x, so now this is our length unit, to a large number, 2 to the p minus 1, times the derivative, 2p derivatives of the function u. Because this guarantees a few things for us. So first, notice that this delta x is our modification to the equations. These are the equations we're iterating. Let me forget about that. This is the original equation we want to iterate. And we have to remember that numerically, we're never iterating the equation we want to iterate. We're iterating the equation we're iterating, which is an approximation to the original problem. So let's say you have introduced, I don't know, a third order accurate iteration in time, and you have worked very hard to have fourth order accurate these derivative operators in space. So your scheme is at best third order, because your scheme is governed by the lowest order, if everything goes work, by the lowest order of approximation. You have third order here. So that means that, if I forget that, this thing is approximating that problem to third order. But if I put delta x here to the fifth power, I'm only changing the problem I'm solving to fifth order accuracy. Therefore, this problem has not changed its approximation to third order to the original problem. So this is a trick that you can add, always consistent with the level of approximation that you want you're doing for your original problem, but it has as an added bonus the ability to control the high frequencies. Again, you have to be very, yes? Oh, excellent question. So that helps that you have this length scale. Have we not put this length scale, let's say, and you had stay in the second order, the problem is more like a parabolic problem. And so then we could have completely changed the hyperbolic structure of the equation. Here we have that. And yet, indeed, there is some diffusion part that you're effectively adding in, but it's monitored or governed by this delta x. So when you look at like the CFL condition, then it doesn't change. Of course, provided you have used this epsilon, this epsilon cannot be arbitrarily large. You have to analyze the bounds of that epsilon. And that first paper comments on that. But yeah, so you don't change it. Right, so again, the hyperbolicity is here. Now this is a discretization. What you're adding is at the level of the truncation of your problem, which has already been, it's already different, of course, from this one, because this one doesn't have it. You're just playing around with the truncation terms so that they don't add up destructively or constructively to give you a destructive contribution to your code. So we mentioned CFL condition a few times. Do people know what that is? Yeah? I don't need to say it? Okay, good. So now, again, you have exactly the same problem. If you're going to follow this route, then you're going to be trying to make, notice here, put approximation, the discrete concept for time iterator, for the space iterator, but I haven't given you this one. You could add these, and if your derivative operators do not satisfy the property that we want, that the contribution of this term is strictly negative, then you're going to be spoiling everything you're trying to build by this addition. So that paper, for instance, will give you the particular operators that you need to use for adding this problem. And you can see, again, so then one neat thing of having a code and playing around with it, just you can put it, set epsilon to 0, see how the solution that you obtain behaves, then turn it on, and then you can see its influence and how it works. And also, if you take it too large, we're going to this last question, you're actually going to break the code, because this introduces also some constraints. You cannot put it arbitrarily large. Any questions? No? Okay, so we're going to keep going back and forth on this, and then we're at the same page to start moving on. So let me introduce one last concept, something called so maximally dissipative boundary conditions. When I told you that statement that if you use these operators, you iterate it with at least third order in time, and you have a strongly asymmetric hyperbolic system of equations, things will work if you follow the rule. I did not cover boundaries. So you also need to worry about boundaries. If the boundaries are incorrect, of course, that's not going to be satisfied. That theorem assumes that you know what you're doing at the boundary. So let me tell you how we can treat boundaries. So we're going, again, let's imagine that we have a system of equation. Which that's a matrix. So we go again through the iteration or the energy. And now I'm going to be very quick. I'm going to be ignoring factors of 2. So let me take the time derivative of that. Well, nothing else. And here is where we can, again, introduce our representation of U and A in terms of a diagonal. So we're going to be able to write the following. So let me let me use a simple example. So let's say U comma T is U comma X first. Yeah, let me just concentrate on this one first. So we worked on that, and then we found out that this is U squared left and right for that problem, which then says U squared evaluated at the right minus U squared evaluated at the left boundary. So now I have a 1 here. So which direction any perturbation will be moving? Will it be moving to the left or to the right? Any guess? We have 50-50. So if I have, let's say this is my left boundary, my right boundary, and the solution to this, remember the solution to this problem was any function of t plus x. So so it's going that way, right? Which means physically we have the freedom to give boundary conditions here, but we don't have any freedom to give it here. The solution here is completely determined by what's going on in the interior. So the flux is moving from right to left. We better not touch this one. If we do it, we're going to be introducing generically an inconsistency. first, well, if we knew what we should be putting here, we wouldn't be solving the problem to begin with, because we would know everything that is in here. I could just iterate, follow this to the past. Second, even if I knew exactly what I should be putting here, I know exactly at the analytical level, but not numerically. So we'll introduce a small kink, and these kinks will kind of will exacerbate with time. So here is where we can put the boundary condition. And if I look at our expression, we know this. So we cannot do anything on the left. We can give whatever we want on the right. So maximally dissipative boundary conditions, and this is a kind of confusing name because it doesn't have anything to do with maximal and very little to do with dissipative. But what it's telling us that if the value of the function, let's say u at the right, we choose it if well, this is square, so I don't need this. So if we choose it this way, that's what I want, then we're guaranteed that this is bounded. So this is a scenario where the energy in the system cannot ever grow. If we see any growth whatsoever of energy, it's something else going wrong in our implementation. So this is a family of boundary conditions that will guarantee, as I said, that your numerical solution should be well behaved. Of course, I was stretching the truth a little bit, well, actually quite a bit. All these results assume that you're dealing with a problem that is at most with varying coefficients depending on time and space. So we have a problem like so. Something of this form. So it's a linear, still it's a linear problem in U, but we can have non-constant coefficients multiplying them. That's the best we can do. If we go to the nonlinear, we don't have results even at the analytical level. But so this is the strongest footing you can start your simulation. You can start your construction. So if something is known not to work here, well, it's not going to work in general. Anyway, so that's, I should say that's important. And the one thing I also should comment on is what happens in the general case. So if we have something of that form. So now if we have, say, in 3 dimensions, you have derivatives with respect to x, with the y, and z. So everything I've been describing has been in 1 dimension. So this is where the difference between strong and symmetric hyperbolic shows up. In the case of strong versus symmetric, it boils down to the following. Remember, we said strong and symmetric in 1D, they are equivalent. This matrix can be diagonalized. The difference between strong and symmetric is the transformation that to diagonalize a matrix in the 3D case is the same for all dimensions. So you can find one general transformation that transforms all of them to a diagonal form. In the strong case, the transformation depends on the direction you're talking about. But beyond that, there is not much that you lose. So in general, we're going to assume that it's the same. So any questions? Okay, so now we have gone through everything. So we're assuming we write our system in first order form, and that we can guarantee, or that we're going to try and guarantee, that the system satisfies this hyperbolicity condition. We have a series of techniques that are robust to try and put them numerically, and then we're off to the races. So now I'm going to try to pull things back to generativity. I'm going to say a few things, and then we're going to break. And then describe some of the peculiarities that generativity has in store for our numerical implementation. So first, I have a piece of good news, which is generally the kind of problems we're dealing with And I'm going to throw away a pi, because if I was throwing 2, why not throw a pi as well? So let's imagine that. So those are Einstein's equations. Here we have our stress energy tensor. Here we have our kind of geometric terms. And we want to study the couple problem. The one thing that was great, or that is great, is if you study the kind of problems we're interested in this course, where say TAB is like a perfect fluid that might be magnetized. So we have a perfect fluid here, and say the the EM contributions. So these come in the form of 6 rho, P, U, an equation state, undifferentiated. And with respect to E and M, this is also has contributions of the electric, say, and magnetic field, undifferentiated. The equations of motion of our stress energy tensor are determined by the conservation of the stress energy tensor, or the Navier-Stokes equations, or whichever ones, well, not the Navier-Stokes, the relativistic hydro equations. This implies that now the equation of motion have at most first derivative. Let me just call it the fluid. So Einstein's equations, also the GAB, has second derivative. So GAB, the Riemann tensor, has in it second derivative of our metric tensor. So with respect to the fluid equation of motions contain first derivatives. The metric tensor has second derivative. The coupling between the equation of motion for the metric tensor and the fluid is through no derivatives, right? So they belong to the lower order terms. So as far as we are concerned, for the general discussion, we really cannot care about that TAB. Well, that, of course, going back to the previous question, the particular solutions care intimately about that. Whether we have a star there or not will determine the solution in a significant way. But with respect to the propagations or the behavior of the metric tensor, the fluid couldn't care less. I mean, the existence of the fluid, we don't care. And beautifully, the same goes true for the fluid. This has first derivative of the fluid, but with respect to the metric, has first derivative of the metric tensor. So as you know, the Christoffel symbols show up. The volume element determined by the metric show up. And these are things that you're going to see throughout this course. But because they don't show up, we don't see second derivatives of the metric, then similarly, for the equation of motion of the stress energy tensor of the fluid, the metric comes in the lower order terms. And so the beautiful thing is that you can develop a code for this independently of a code for that. So if at the end of the course you develop or you are get familiarized with either one of the options, doing the other one is not a big deal. There are counterexamples to this. The counterexamples would be if, for instance, you describe the stress energy tensor not for a perfect fluid, but for a viscous fluid. As you might have seen, that involves higher derivatives of your fluid variables. Now the coupling begins to be slightly more delicate, and you need to analyze how disconnected are with respect to the principal part. There are also other metric theories of gravity, which is not Einstein's general relativity, where the coupling has higher derivatives. And now you have to be worried about it. So when you violate the equivalence principle, that's an example. So at the end of the day, this observation is all all has to do with the equivalence principle. Because Einstein equation satisfied that principle, then this is true. So the good thing is that I'm going to be discussing this, completely ignoring this part for the time being, and I'm going to discuss a little bit of this, but Charles and others will discuss a lot more. You're going to talk, you're going to get that part, and also Pascal is going to be talking a lot about fluids and their peculiarities and how to deal with them. So again, any questions, ask me. So I'm going to be trying, because the description of Einstein theory of relativity and how we face them is much, much broader than what I'm going to cover today. If you have questions, ask me. I'm going to just primarily focusing on what kind of things I think are going to be useful for you in the coming weeks. So that's these Einstein equations, and again, for the reasons that we talk about, I can put a 0, or I can put the contributions of fluid for all intents purposes. It doesn't matter at this point. If there is ever a point where the source plays a role, I'll let you know. But by and large, we're going to concentrate on this. So this is the so-called Einstein tensor, which is expressed in terms of the Ricci tensor and Ricci scalar this way, and this in its own, and that are obtained so this is a particular trace of the Riemann tensor, and the Ricci scalar is a trace of the Ricci tensor. This is what satisfies the divergence equal to 0, so we call them the Bianchi identities. But if we're going to have in the right-hand side a TAB, the TAB that satisfies its conservation, so the divergence of the stress tensor is 0, then this divergence has to be 0. So Einstein, for a long time, was working just with this piece, not including that one, and then he noticed that he needed to add some piece to ensure that the divergence being 0. So this satisfies that. Written this way, the equations are extremely simple, but of course they hide all the mess inside. The one thing that you face immediately is when trying to think about how are you going to study the future evolution given in some initial state is what is even the future? Coordinates have not been defined here. We don't have any way whatsoever at this level to determine or even begin to think of how we're going to pose our problem. So we actually have to kind of work our way backwards. We have to undo Einstein's hard work on writing this in covariant form and kind of break it apart, and then try and introduce some notion of time evolution. So for that, and of course, on the way to doing that, we're going to try, in as much as we can, keep the geometric notions handy for our use. So the first thing is, well, given a space-time, and let's imagine this blackboard is a space-time. Time is, the Big Bang was somewhere at the very bottom, and who knows what happens up there. But we're kind of somewhere in between, and we want to say at some given time, or some given instance, we will know everything of that, what's going on for every event of the space-time at that given instance of time. Of course, I'm an observer. The only thing I can say is something about my local neighborhood. So we're going to have to introduce some ad hoc formulation or some ad hoc way of introducing some time. So let's imagine I introduce some slice here, and another one here, etc., labeled by some arbitrary label, which I'm going to call it T. Each of these will be a hypersurface. Let me call it sigma. I'm going to put a T underscore there. Sigma T plus delta T. If I go too fast here, make sure you stop me. These are not typical things that you might have seen in the past. So make sure we get to be in the same page here. So on this hypersurface, I can define some natural context. So I define this. So the first thing I want to make sure, at least, is that this hypersurface is a sane hypersurface, because I still don't know if this hypersurface is null, where a null vector, photons propagate tangential to it. It could very well be. We need to check that this is not the case. Or it could be time-like, something that a geodesic or an observer will move also tangent to this hypersurface. We don't want that. We don't this to be a bona fide time, something that we say, well, this time this is happening, and the connection between points. So if we think at each point our null cone, within the null cone we can send time trajectories at the boundaries of the null cone. We can say photons, and anything that is outside that cannot be connected with each other unless I'm communicating at a speed faster than the speed of light. So we want to know that if I draw at each point the local cone, that we see this. The first thing we have to is to recognize what we're going to call inside the cone, tangent to the cone, or on this plane. So for that, I'm going to introduce some signature. So I'm going to say that locally, my metric is like that, so it's flat. So that one premise, again, through the principle of equivalence, that if I go arbitrary local at any given point, I can always choose coordinates that make the space-time be exactly flat at that point. So these are the coordinates I'm choosing, and I put in a minus sign in the time coordinate, and that's because it's the particle convention I use. Particle physicists are fond of using the opposite, and I think they're wrong. No, just kidding. That's a convention. So given that hypersurface, there are concepts from just geometry we can define without knowing anything, or not knowing much more. At any given point, I can ask what's a normal to that hypersurface. I'm going to call it NA. So this forms, if you want, 90-degree angle with respect to that hypersurface. And that's because we have a surface. I'm assuming that the surface in our spacetime, if I say t equal constant, that gives me that hypersurface. And the normal to it is I'm also quickly, and I have already done it, beginning to use some notation. This index here, it's an index that denotes a vector or a covector where it's down or up. We're not going to be making a lot of difference, but this is a covector. So this lives in the hypersurface. If I raise it, I'm going to have to see what happens with the rest of the spacetime. On that hypersurface, we can have coordinates. So I'm going to have, say, coordinates x, y, z here. But absolutely no one forces us that if I follow this normal till I meet the next hypersurface, no one is forcing us that x, y, and z have to be the same. So this could be a different one. We might actually want that. Why we want that? Let me give you this example. Suppose our slice would have been something like so. This is the next hypersurface, etc. Had I taken this normal, had I taken that convention that along the normals my coordinates stay the same, well, very quickly I'm going to be in the situation where at that point I have the same coordinates even though they came from two different events. So so at the same point I have two different set of coordinates. So this is an example of coordinate singularity. So we would want to keep enough freedom under our control, or at least our control to monitor it, to avoid these kind of scenarios. So I can say, well, at least I can do the following. I can say, well, given if I go from here to there, I will advance in coordinate time, or in coordinate lapse, an amount delta t, because that's the labels I use here. So if I ignore what coordinate labels I've given to these 2 points, but I ask how much in delta t I have gone, that would be delta t. But of course, we know that that makes no sense. That's not physical. What would make sense is to have someone be there and move up and keep track of its proper time. So proper time, let's call it d tau, is we're going to monitor it with a new function, with a function we introduced, this alpha, which is called the lapse function, which measures precisely what we just said. If we go up along the normal till we meet the next hypersurface, that times the delta t in our arbitrary chosen label should give us the proper time. So now we want to say, well, suppose I have given these coordinate labels here, and I go to the next hypersurface, and I find the next, or decide that this is the point that have the same x, y, z coordinates. So I need a parameter, or a vector, rather, that tells us where that is. So this will be a vector pi, beta I. Question? No. Which is going to be, for us, our shift vector. So that's as far as the relationship between one hypersurface and the R1 is defined. Now I'm going to say at each given hypersurface, I'm going to try and take distances, so I can measure the distance between, say, that point and that point, and I'm going to say this point, the metric that helps us define that distance is HAJ, and as a piece of notation, you will see it typically written in terms of as HAJ, or gamma IJ. It's just a matter of choice. Also, this, depending on the literature you read, might be given the label N, the lapse function, or the vector beta is sometimes defined as NA. So you'll find one or the R1, and typically they come in this pair, N and Ni, alpha and beta, and it depends who you read. It might be H or gamma, and depending on what I'm talking about, I'll use one or the R1. Incidentally, a very good resource, very good presentation for this is this book by Miguel Alcubierre, the 3+1 Introduction to 3+1 Numerical Relativity. There are several books. There is another book by Thomas Baumgartner and Stu Shapiro, another one by Carles Bona, Carlos Palenzuela, and some other Bona, but I can't remember his name. And there is a fourth one, I can't remember that one. But by and large, those are the books that you can have. I particularly like Miguel is very well presented. What he presents, it's very good, well done. Okay, so by definition, a solution to Einstein's equation is given by that some metric, GAB, which is a metric of the full spacetime. So if someone tells you, I have the solution to Einstein's equations, they will give you the metric at the full set of events that define our particular manifold from the very beginning to the very end. But we're trying to make contact with this concept of things evolving in time. So what I want to do is rewrite this GAB in terms of every concept that we have introduced here. And let's say, in general, if I take two arbitrary points, these 2 points, and I ask, what is the distance between those 2 points? That's going to be given so ds squared, in terms of the full metric, is simply, by definition, right? If you take displacement dxa along all 4 possible directions that will join the first point to the second one. That's that metric. In terms of the other concepts we have introduced, there's going to be minus alpha square dt square. That's measuring how much it takes the distance to go from there to that. And now we have to account for the other piece we have, plus so let's see what we have. So this was obvious. This was just the proper amount of time. We went from one to the next one. And then the rest we have that tensor that is a 3-dimensional tensor. This is a 4-dimensional. This is only 3 that lives on each given hypersurface, which I said help us measure distances on a given hypersurface. And we have to then multiply just very much as we did here, the displacement. We're doing this, but we have to remember that our labels between 2 different hypersurfaces change by this vector beta. So that accounts for that. So we have the displacement from the point we got, but then we need to add the shift for the mislabel between going normally, because here we went in normal direction, and this extra further shift between the point we land and the normal, and then the one we want to measure the distance with respect to. So that's called the 3+1 decomposition. So far what we've done is just setting up the basic skeleton. We recognize that the full form metric can be determined or can be re-expressed between concepts or things that are intrinsic to hypersurface and things that are off the hypersurface. That is, of course, still a very far cry to re-express in Einstein's equations. We need to introduce further concepts. What we're going to try and do, and we're going to succeed in doing, is to then think of the evolution of the space-time, or the evolution of this metric tensor, as something that has Wheeler called geometric dynamics. So we want to know that given each hypersurface, with some properties, how it essentially seems to evolve to the next one by a series of evolution equations, which we are going to derive from the Einstein's equations themselves. So one further concept we'll introduce is that of this called the extrinsic curvature. The extrinsic curvature is related to, if you want, this one, and it's the other, given a particular hypersurface. Mathematicians or in geometry introduce 2 concepts. One is called the intrinsic geometry, and the other one is the extrinsic geometry. This one is intrinsic to the hypersurface. It knows nothing as to how it's embedded in the rest of the space-time. So the intrinsic geometry of this sheet of paper is just flat. I mean, I can see the squares, they all form 90-degree angles, etc. But now whether this sheet, which has intrinsic metric, which is flat, is embedded this way or that way in the extra dimensional space-time where it lives in, we need another concept for that. Of course, we introduce this vector n. And whether this vector varies or not, as seen from the higher dimensional space, is what we were after. So there is this thing called the extrinsic curvature. Let me just read it this way. So it's the covariant derivative of the vector n with a minus sign. Again, that's a convention. That's extrinsic curvature. We're going to try and make use of that heavily in the next class. And it's related to the rate of change of n as seen from the full space-time. And one thing I need to mention is that this covariant derivative nabla is a derivative naturally associated to the full metric. So it's the one that satisfies that condition. We're later on going to introduce this one. I'm going to call it DI, which is the derivative naturally associated to this will allow us to keep as much as geometry parlance as we can, even after having defined breaking up all Einstein's equations that way. And the last piece of notation that I already use to some degree is where whenever I write A, B, C, the top letters of the alphabet, these are usually 4 space-time quantities, time labels. And when I use I, J, K, kind of the second half, this will be 3. And this will be space. So before I start the next one is a bit heavy. So I think I'm going to stop here. If you guys have any questions, please ask. No? Everything clear? Oh, well, tomorrow is going to be heavy. It's going to be much more difficult. But so if you have questions about this, make sure you ask me. We haven't gone far at all, but tomorrow we're going to use all these concepts to rewrite those equations. But maybe I can kind of anticipate what we're going to do. We're going to write all. We're going to work really hard to rewrite those equations in terms of something that will look like the following. dt so we're going to see that the rate of change of the intrinsic curvature or the intrinsic metric, or as mathematicians would like to call it, first fundamental form, is related to the extrinsic curvature, the extrinsic metric, or the second fundamental form. This will be, or is essentially by definition. By this definition, we're going to be able to derive something pretty much like this one, schematically. By using Einstein's equations and some relations called the Gauss-Cauchy relations, we're going to be able to obtain something of this form. So it's going to be derivatives of alpha, but then we're going to recognize terms like so. Yeah, so let me do it that way. And this will be that width where alpha and beta are free. So if someone hands you the right set of coordinates, or somehow a particular prescription to obtain alpha and beta, the equations of motion for these equations we're going to be able to write it this way. These are the so-called ADM equations, which people use and derive first, Arnold with Desser and Misner, thinking of trying to write things in a way that will help in trying to see if they could understand the connection between Einstein's equations and quantum mechanics. And for that, again, some evolutionary system is convenient to have in mind. This is the system of equations that people use in numerical relativity for a very long time. Till in the late 90s, this guy, Kreis, and Ortiz pointed out they are weakly hyperbolic. They're weakly hyperbolic for several reasons. One is, and this we'll discuss tomorrow, if you rewrite this R, so notice this is like time derivatives of H is K. If I take another time derivatives of this one, will give me second time derivatives of H is given by R. In R, we're going to have things that have second space derivative, let me just call it k of hij, that's pretty good because it's looking like a wave equation. But then there are other pieces. And these are offending pieces. These are the pieces that work against the hyperbolicity properties. And also, it's not true that this alpha and beta can be completely freely chosen. So we're going to have to add some extra information on how to choose this in the most convenient form. And of course, they're weakly hyperbolic in the general three-dimensional case. If you were to use it in spherical symmetry, they're perfectly fine. The violation of the conditions for having a complete set of eigenvectors only happens in the general case. In spherical symmetry, everything is fine. And also in spherical symmetry, you can even ignore these evolution equations altogether. You can just obtain it through constraints. So that's something else we're going to discuss. But this is what we're shooting for. And we're going to do that first class tomorrow. Thanks. No class.